Hey guys, it's Chili here, and let me tell you, I am pumped because I've got a bit of a treat for you today. I'm starting a new series, and that series is going to be, I guess you can tell if you're looking at the screen right now, it's all about SSE and optimizing code. Well, it's not all about SSE. I'll talk about some other considerations along the way, but it's going to be mostly about SSE because SSE is you can make routines that are so fast it'll blow your fucking mind. So I want to share this with the world at general. The people must know about the SSE revolution. Some of you might be wondering about hugs. Have I canceled that series? No, I have not. I've gotten other things have come up. I've taken up my time, and my interests have kind of been distracted for a while, but I've definitely not canceled. I fully intend on finishing that series. But, for the moment, I want to do something else, and I could just wait and start up just make no tutorials until I'm ready to start Hugs again, but I figure, why not start a second series running parallel to Hugs, and that way I can still keep the videos coming. This series is going to run parallel to the Hugs series. And to be honest, I was actually planning on covering this topic throughout the Hugs series as like a part of it, but it's really, the topic is too big to form just a small part of one series. It deserves its own thing. It is its own thing. You are your own thing, SSE. You do you. So we're going to be doing it in its own series. I've checked YouTube, and I've found that there aren't too many goods. Well, I shouldn't say that. That's slanderous. But I can't find too much information on SSE programming. So now's my time to shine. I've found my niche again. So yeah, I guess I'll just get into it now. So what is SSE? Well, it's an acronym. It stands for Super Strong Erection, because that's what I get whenever I think about programming in SSE. And when I'm actually programming, you don't even want to know what's happening. It involves liquids. Anyways, that's not what it means. It stands for Streaming SIMD Extensions. Yes, it's an acronym within an acronym. BBBQ. The extra B stands for BYOBB. What does that B stand for? Oh, that's a typo. So, streaming doesn't matter. Extensions doesn't matter. The important part of this name is the SIMD part. The acronym within an acronym. And what it stands for is Single Instruction Multiple Data. That's the technology paradigm, the programming paradigm that is represented in this instruction set. And it allows you, the idea is to perform multiple operations in a single instruction. Single instruction, so one operation, but performed on multiple data points. So instead of performing one multiply, you perform 4 at a time, or 8 at a time, or 16 at a time. And obviously that's going to be way faster. If you're performing 4 times as many operations, you're working 4 times faster. Seems obvious. Well, quickly to overview, SSE, in the processor, it has its own set of registers. They're called, XMM0 through XMM7. Now, if you generate your code in 64-bit mode, then you actually get 0 through 15. You get double the amount of registers, but we won't worry about that right now. And these registers, their width is 128 bits. That's fucking wide. Think about a 128-bit number. That's like 34 with like tons of zeros after it. I can't remember how many. I think like 37 zeros or something like that. Something stupid like that. Anyways, it's a fucking big number. So you might be asking yourself, well, Chili, why do I need to program or to code with 128-bit numbers? That doesn't help me. I'm not going to need to store a value that high. I'm never going to use that whole dynamic range. And no, you're not. Of course not. Like the move from 32 bits to 64 bits, like some people would say, well, you're doubling your bits, you're going to double your speed. That's not how it works. I mean, most programs don't really need the extra 64 bits. The reason why we have moved to 64 bits mostly is just to increase our memory space more than because we need 64-bit width of instructions. So moving to 128-bit is obviously not going to benefit any but the most niche of applications. But that's not what we do with this 128-bit register. Oh no. What we do is we pack values into our register. So let me show you something here. So this thing that I'm bringing up here represents a 128-bit XMM register. And it's divided up into 8-bit regions, each region holding an 8-bit value, a byte. And we can perform operations to add each byte separately between two 128-bit registers. So we can add 16 bytes to 16 other bytes in a single clock cycle. And that is hella fast. Just one example of how SIMD works. So you got two registers and you're adding vertically. Almost all your operations that you're going to be doing are vertical. So you want to add, so you add the one in the, if this is the high and this is the low end of the register, this would be bit 0 and this would be bit 127 at the top here. You're adding each byte to its corresponding byte in the second register. First register to second register. In general, if you want to add, like, I want to add diagonally, or I want to add crosswise like this, there's no easy way to do it. You're going to have to do that in multiple operations. So with one of the big battles in SSE programming is getting your data lined up properly. You really have to think of how you're organizing your data to minimize all the shuffling around you have to do. But this is the basic concept. You pack data types, multiple types of the same data into registers, and then you process them together. They also, they have to be, I think all the instructions require the data to be the same. So it has to be all bytes or all words or all single floating points or all double floats. You can't have I'll have a double word here, and then I'll have a word, and then a word, and then I'll have a byte, and then I'll have a word, and then I'll have a float, and then a byte. That's not how it works. It's got to be all bytes or all floats. That's what you get. I guess I'll show you the code that we're going to be working with. This is going to be up on GitHub. It is up on GitHub, and I will put the link in the description so you can pull this off of GitHub. And yeah, you clone it, I think is the term. I don't know. Whatever. Clone this and you can follow along or not. You can just watch me. It doesn't matter. Very basic framework here we have. Got some images we're going to be using. Here's a log file that is going to store benchmarking data. Because rule number 1 of optimization is always benchmark. Because you'll make assumptions. You'll be like, I believe this way will make my code faster, and you'll code it up. And then you'll actually benchmark it, and you find out that no, the compiler was doing it faster all along. So rule number one is benchmark everything. Assume nothing about the performance impact of your changes. Always benchmark. That's rule number one. So most of our work is going to be in the surface class. I've added a shit ton here of functions, and they're basically, for the most part, they're filters, full screen filters, and later on we're going to have some like draw rectangle and blit functions, but lots of filters, lots of blending, and this is going to be what we use to practice SSE. It's a perfect playground to wet our feet, as it were. The thing about SSE is it works best when you have a lot of data. You need lots of data. And then the data has to all be contiguous in memory. It can't be all over here and there, and that's bullshit. It's got to be all lined up, and it has to be it's got to be homogeneous. Homo. Yes, homo. Just think, when you think SSE, think yes, homo. You want your data all to be the same layout. And pixels, or graphics data, surfaces, they fill all these requirements. There's tons of pixels in a back buffer. They're all contiguous in memory, and they're homogeneous. They follow the same ARGB pattern throughout memory, or BGRA, depending on how you're lining up your bytes. So that's why I chose this topic for the first series of videos on SSE. So I've got a bunch of functions here. And the first one we're going to look at is the simplest thing you could think to do on a whole surface, and that's just clear the surface. Set it all to zeros. So let's bench this. Let's see how long it takes to clear the whole surface. Mind that my numbers are going to be probably a little off because I'm running my my capture software at the same time, but shouldn't be off by too much. And of course, it does not matter because you're going to have different computers than me either, so it's not like you're going to be able to compare yours directly to mine. So what we want to do is we want to go clear. And we'll build that. And then we'll run it without debugging. And we'll get a black screen like this. I've set the size of the back buffer for this framework to 1280 by 720p. So it's a little bigger than the other stuff we've been doing in the tutorials. Let's look at the log file. We can just click it here in our resources, and we see it takes about 100 microseconds. These are in units of milliseconds, so 0.1 milliseconds, 100 microseconds to clear the entire back buffer. All right, I guess that's okay. We don't really have anything to compare that to, so sure, I'll buy it. Now let's take a look at the SSE version of clear. This one just calls memset, so we don't really know how it's doing it. It's just doing it somehow. The SSE I've actually coded myself. And it works like this. Geez. All right, so before I talk about this, there's one other thing I want to talk about. Let's take a look at another function here called fill slow. If you look at memset, the parameter here, the value that you fill into memory, it says it's an int, but in actuality, memset sets bytes. So this value here, it's not going to set 4 bytes at a time. It's setting 1 byte at a time. So for example, memset 0 is exactly the same as memset, for example, 256. Build that. Still black, right? Or I could go memset, let's see here. I'm trying to think of a color that has 0 blue, and what does red and green make? Does that make yellow? I believe it makes yellow. So if we go yellow, the low byte should be 0, and in fact yellow gives us a black screen. Whereas if I went blue, I should get a white screen. Because the low byte is going to be FF. And when you fill the entire thing with FF, you'll get white. So memset is okay for setting to black or white or any gray value, really. But if we want to set to any arbitrary color, we can't use memset. So let's write our own filling function that will fill the memory with double words and not bytes. And what we would probably come up with is something like this. Just simple nested loop, put pixel. Now you might have a premonition about how the performance of this function is going to be based on its name. But let's run it anyways. So fill slow. Remember, filling with bytes, 100 microseconds. Fill slow gives us 630 microseconds. That's over 6 times slower. And remember, we're still filling the same amount of memory. We're just filling it in chunks of double word instead of chunks of byte. So that's not really that good. I mean, it's pretty terrible when you think about it. And you might be saying, well, Chili, you're putting a function call inside there. It has to jump to that function for every single pixel. And true, if that were the case, it would slow us down. But this put pixel is actually being inlined in here. If I were to replace this put pixel with the call with the body of put pixel. Now let's just go in here. Where's put pixel? Here it is. So let me just, for argument's sake, replace the function call with, where is it? This way. Replace the function call with the actual statement that the function contains. And we'll run. Stop. And look at the log file. Still the same result, no change whatsoever, because of course that function call was being inlined. The problem here is, well, let me just go back, let me replace this. Every pixel, we have to calculate the address of the pixel to fill. So we've got to take y, multiply it by some constant, then add x, then add that result to the address of the beginning of the buffer, and then we can move our data. And that's slow. So what we do instead, the alternative is, instead of looping on indexes, we loop on pointers. So we initialize our pointer to the beginning of the buffer, and we also initialize an end pointer to the pixel or to the byte that follows the last byte in the buffer. And we keep looping, we keep incrementing the pointer until the pointer reaches the end of the buffer. And because we do this, we don't have to calculate the address every iteration. The address already exists. The address is just the loop variable. They are one and the same. So if we replace fill slow with plain old fill, build this motherfucker again, and same result, of course, green screen. Look at the log file, and we're back down to 100 microseconds, which makes sense when you think about it. Because, yeah, you're still filling the same amount of memory. So why wouldn't you have the same time taken? And that's what you get. So the moral of this story, I believe, is obvious, and that is especially when you have a loop body that doesn't do much work. You want to avoid looping on indices, and you want to loop on pointers, because this overhead can actually become quite large in comparison to the operation you're performing. So that's my optimization tip number one, particularly for tight loops that run a lot. Loop on pointers. And now that enables me to talk about the SSE implementation of clear. Because as you notice here, again, we're looping on variables. We're not looping on an index or indices. We're looping on one pointer. So where to start? First of all, like I said, SSE works with 128-bit values, or smaller values packed into a 128-bit register. So to use SSE, you need a new data type. And that data type is the $M128. There are two versions. There's a version with an I and a version without an I. The version without the I is for floating point values, so singles or doubles. The version with an I is for integer values or just bit values. So we're going to be making a lot of these. And of course, we have a pointer to that. So we're going to cast our buffer pointer, which is a pointer to color, and we're going to cast that to a M128. And again, with the beginning and the end. If you don't know what this is just another way of casting. I could have easily just written the C style cast M128, and it would work exactly the same, no problems. But sometimes I feel like being a little fancy, using the C++ style casting. But it is long as fuck. But what's done is done. So, what are we doing in this operation here, in this routine? First, we're creating a 128-bit variable, and basically these things end up becoming registers. So the compiler just turns them into registers in memory in most cases, unless you have so much that it can't fit in all the registers, and then you overflow your registers, you get register thrashing, which is not good. But in general, these are just registers. So we create an XMM register and we fill it with 0. And then in our loop, we store that into the memory pointed to by I. So we're storing 16 bytes at a time, or 4 pixels at a time, with this operation here. So 4 pixels at a time, that should be pretty damn fast, right? Well, let's give it a shot. So we'll go clear SSE. And we don't need a parameter. We'll run her for a second. We get the black screen as expected. And looking at our data, well, we are actually like 28% slower, or maybe 25%-ish, I don't know, slower than the case when we just called memset. So memset is actually faster. So you might be wondering, well, geez, if we're moving 4 pixels at a time with SSE, what is memset doing that's so goddamn fast? And, well, let's take a look at that. An important part of optimizing, especially optimizing with SSE, in my experience, is inspecting the actual instructions that the compiler emits. So we're going to try that right now. We're going to set a breakpoint, and we're going to start with the debugger. And the first thing you notice is the breakpoint isn't being triggered. And you might say to yourself, well, geez, Chili, I could have told you that breakpoint was going to be triggered. You're not in debug mode. But we don't want to debug in debug mode, as counterintuitive as that sounds, because debug doesn't generate the same code, doesn't emit the same instructions as release. It emits way slower, lots of safety and checks and all sorts of junk that it inserts in there, all sorts of optimizations that it doesn't undergo or undertake. So we want to inspect the actual generated instructions in release mode, and we can do it. But the problem is, the reason why this isn't being triggered isn't because we're in release mode. It's because this function doesn't actually exist. Or to be precise, it's being inlined. So this function is going to be inlined into here. Oh, wait. Okay. Well, first one reason why the breakpoint might not have been triggered is because we weren't actually calling the function. So I'm going to call the function now. And again, the breakpoint isn't being triggered. So the reason is because that function is being inlined in here, and that is probably the composed frame is probably being inlined in Go as well. So what we could do is set a breakpoint at Go and try to trap it from there, or the method I prefer is just to tell the compiler, don't inline this function. So we go decal spec no inline. And that tells the compiler, don't inline this, dude. Just leave it, man. Just call it like a function. Be cool, bro. So if we start debugging now, we trigger the breakpoint. And it is at this point that we go to disassembly. We don't have the source for memset, so we can't step into it. We just have to go to disassembly. And we step, and when we hit call, we want to step into, and that'll jump to memset. And then we got another jump for whatever reason, I don't know. It's a thunk or something, I don't know what it is. I don't know, and I don't care. We got tests, some stuff, more tests, more jumps. Move, push, move, and here is where the magic happens. Rep stos. So the stos instruction, store string, is an instruction that has actually existed in x86 since, like, I believe the beginning of x86. I'm not 100% sure, but it's been there for a long time. Probably since like the inception of the chip. And what it does is this one instruction will fill the entire back buffer in a single instruction. And you might say that's super fast, Chili, but it doesn't do it all at once, obviously. It enters a hardware loop in the CPU. It stops fetching instructions, and it just fires the specified byte value into memory. So you have to set up your registers. I believe one of the registers, probably EDI, will be, I'm guessing EDI is probably the count, but I could be wrong. Oh, maybe C, because C is count, right? So probably ECX is the count. That's how many bytes you want to move. And EDI maybe is the value, the data, which would be 0. Is it 0 here? We can actually look. No, it's not 0. Okay, well, I don't know. I don't know which registers hold what values, but you set your registers up with the data that you want to fill and the count, and then you execute the instruction, and the CPU enters a hardware loop where it decrements the counter and fills in the data in the pointer. Yeah, you've got to also set the pointer. You got to set the data, you've got to set the pointer to the start address, and you got to set the counter of how many bytes to fill. And it uses that information to fill out a block of memory. Now, the thing about rep stos is it was an instruction intended for exactly the purpose that it's being used here, which is to fill a block or a string in memory with a single value. But with the advent of MMX and later on SSE, where you could move 64-bit data and then 128 bits of data in one instruction, it turns out that rep stos was actually slower and it went into disuse. In a lot of situations, it was a lot faster to use SSE, for example, to move your data. However, it turns out that Intel made a change starting with, particularly with, where is it? Ivy Bridge, and it's called the Enhanced Rep Move SB and stos B operation. So when you're using the rep operation with the stos, particularly for bytes, you get high performance. Basically, the CPU enters like a whole different mode, and it moves data at the most efficient way possible. And that's good. So what's actually happening in memset, remember those tests that were at the beginning, it actually gets the capabilities of the CPU. It checks to see if those enhanced rep stos capabilities exist, and if so, it uses that. And if they don't exist, then it defaults to SSE. But if SSE doesn't exist, then it tries MMX, and it probably tries a bunch of other things, and a whole bunch of special cases for alignment, and there's lots of fun stuff in memset. But the fact of the matter is, we're not going to beat instruction that has been highly tuned to do exactly what we want to do. Not even with SSE, although we do come close. Now, the surprising thing is, if you remember, I'm just going to get rid of this known line now. If you remember, Phil got the exact same performance as memset, even though Phil does not use rep stos. We can confirm that. We go decal spec no inline, and we can confirm. Just make sure I don't make the same mistake again here. We'll go Phil C. Build that mother, and we'll start. I believe we want to probably set a breakpoint here. And we'll start with the debugger here. We'll inspect the disassembly. And we see that our loop, we're going to add. So this is incrementing the pointer, comparing it with the end, jumping to E3, which is over here. So what this loop is actually doing is it's loading from memory the value of C, and then it's storing that into the address pointed to by EAX, which is I in this case. And this is getting the exact same performance as rep stos, which is a single instruction which puts the CPU into a crazy memory filling frenzy mode. And that doesn't seem right, especially this code doesn't even seem like a good idea. I don't know why it's loading every iteration. It could just load ECX once and then fill that into memory. But anyways, don't worry about that, because obviously it doesn't make a difference. It's getting the exact same performance. And I don't know why, but I have an idea, and I believe it might have something to do with the loop stream detector. What this does is it detects small loops that fit in the instruction queue, and it locks them down so that it doesn't have to keep reading instructions from memory. And that can, allow shit to run faster, ostensibly. And also, I believe that perhaps the micro ops that this translates to might be detected as basically wanting to do the same thing as rep stos, and it might just put the CPU in the same mode that rep stos does. But I don't know. That's 100% conjecture on my part. At any rate, that's what that is. So the moral of this story is, like I said before, you can write code that is slower than what you already had before you started optimizing. And so it's always important to benchmark everything. Because as we see in this case, we've actually done more harm than good by writing our own SSE clear. And SSE fill is the same story. But before I talk, well, let's talk about SSE fill as well. So fill by itself, we've got fill in here. Let's run it. And we'll take a look at the performance. Right, 100 microseconds. And if we go fill SSE, I believe we can all guess what we're going to get here. Take a look at that and look at the log file. 127 microseconds. So, same story as with clear. We can do better with just a straight C function, even without relying on rep stos. So, what was I going to say? I don't know. Just make sure you benchmark everything. All right, so now I'm going to shift gears a little bit. And I'm going to talk about just how we write some SSE code. You may notice some difference from standard C code. Let's dive right in. So the first thing you need to do if you want to write code with SSE is you need to include this include file, imm.intrin.h. That's, I think, the most recent one. That'll give you all the intrinsic functions up until avx2, I think. And also maybe fuse, multiply, add. I don't know. Anyways, you need to include this. And that'll give you access to these functions. They're called intrinsic functions. They're a little different than your standard functions. They don't get called ever. So they don't ever have their own function body. They are always inlined. And they generally all, well, there's a few exceptions, but most of them map to a single instruction. A single SSE instruction has a single intrinsic that is associated with it. The set functions are a little different, but we'll get into that later. So set 0 is an intrinsic that sets an M128 value to 0. So it sets all 128 bits to 0. The mnemonic here is multimedia, probably, MM. That prefix, M's prefix basically everything, SSE, MMX, and AVX. That's just the lingo. Then set 0, pretty self-explanatory. SI is single integer, and then 128 bits. So it's just treating this value as a 128-bit integer, setting it to 0, which means setting all the bits to 0. And store, the store intrinsic here, will emit I believe emits a move DQA instruction, which is move double quad aligned. And it just moves the value of 0 into the memory pointed at by I, moving 16 bytes at once. So, I guess I can, probably be a good idea just to look at the disassembly of this. So we'll go clear SSE. And yeah, I'm moving quite slow at the beginning here, but we'll definitely speed it up as we become familiar with the basics of SSE programming. But for now, we're gonna take it slow. So just sit back, relax, and let the code wash over you. Say decal spec no inline. So we're gonna Like to continue. No. What is your problem, dog? Buffer undefined. Does not take, okay. Well, I can fix this. I'm not sure about the other error, because that was just bullshit anyways, so doesn't matter. And we'll go to our disassembly. And so we see our code here. And what do we got? We got some setup stuff for the loop. Here is where the register that corresponds to 0 is set to 0. It's just exclusively ORed with itself, which is the same as setting a register to 0. And what else we got? Here is where the store SI128 happens. Move double quad aligned and moves the value in XMM0, which has been set to 0, and it moves that value into memory here. The memory pointed at by EAX. So EAX corresponds to our loop I, and so on and so forth. Now, one question you might ask is, okay, I understand move, I understand double quad, that's just 16 bytes. What is aligned? What does that mean? It means that we have to be moving data into addresses that are aligned to the size of an XMM register. We have to be accessing, in this case, storing at addresses that are multiples of 16. For addresses not a multiple of 16, we are going to be fucked. So let's try that out. So we're going to start our pointer. Instead of starting at the beginning of buffer, it's going to start at the buffer plus 1. So that's going to be 4 bytes into the buffer. So if our buffer started at 0, our I is going to start at address 4. And just so that we don't run past the end of our buffer, we're going to subtract 1 from here so that we don't, overrun our buffer. And let's see what this does for our complexion. We don't want to trap that. And we get an unhandled exception, access violation. And it's not going to help us. It's not going to tell us where the error was, but it's obviously right here. And that's because we tried to store to an improperly aligned address. So you have to make sure all your accesses are aligned. It's not a big problem for us now, but it becomes a pain in the ass later on. But we'll talk about that bridge when we cross it. There is one issue that we do have to cover, though. So we can make sure that we are properly aligned within the buffer. We start on, the first byte of the buffer, byte 0 in the buffer, and then we increment the address by 16 every time, right? Incrementing a pointer increments by the size of the data that pointer points to. So incrementing I increments by 16. So we're always going to be accessing 16-byte aligned addresses within the buffer. However, how do we know that the memory that we were allocated, the buffer block, starts at a 16-byte aligned boundary? We can't be guaranteed that, can we? Now, I've never had a problem in my personal experience with my setup with new. So new has always given me a properly aligned memory address. However, malloc has not. So I don't know the rules. I don't know if new is going to give you a 16-byte aligned in all operating systems or for all compilers. I suspect it varies depending on what the compiler is, possibly on what the operating system is as well. And it's not good to leave that just to chance. It'll probably work, but maybe it won't work for some people. That's not good. So what we're going to do is we're going to replace this call with aligned malloc. Size of color times height times pixel pitch. And the alignment is going to be 16 byte. So aligned malloc will guarantee that the memory block that is allocated starts aligned to, well, in this case, a 16 byte boundary. Very important. So we're going to cast this to color. And I'm not going to use C++ style casts at this moment because time is of the essence. I know you're all important people. You got things to do, places to go, people to see, things to see, people to do, places to do. And if we do aligned malloc, we can't do a delete. That'll fuck us up. But we should do an aligned free. I don't know why you need to use aligned free. Like, why wouldn't free work? In actuality, I've used free and it worked fine, but whatever. Might as well use aligned free because it exists. So you should be using aligned malloc, although in my experience, new has never crossed me yet. But I still view it with a jaundiced eye. So I use aligned malloc. And that guarantees me alignment. That guarantees me alignment. That was a horrible accent. It was a horrible attempt at an Irish accent. I don't even know why I tried. All right, so the difference between fill SSE, I'm just completely going off in a new direction now, but the difference between this and this is only that in this one we set the register to 0, and in this one we're setting our register to our color. So we use the intrinsic set1 EPI32. So what set1 means is it means set all of the values packed into this register to one single value. And the type of packing that we specify here is with the thing that follows. So EPI stands for extended packed integer. Forget about the extended thing. It's extended relative to MMX, which is like that's your granddad's technology. That's what that is. So forget about the extended. It doesn't mean anything anymore. But packed integer means we're working with we're treating the register as a register containing packed integers of size 32, which by coincidence or not coincidence in this case is the same size as a pixel. So we're setting the 4 double words in this register to a single value, which is C. All right, and that is the only difference between the clear and the fill functions for SSE. And I think this is where I would like to end this episode. You might be saying, well, Chili, shit, I don't really see the big deal about SSE here. I mean, you're fucking slower than your standard C functions. And you're not wrong for this case, but we've only scratched the very surface. We've only gotten the tip in, just the tip. And where SSE really starts to shine is when we start doing some processing. After all we're doing here is just storing data. So once we get some actual processing going, that's where you're going to see SSE shine, baby. But that's for the next episode. I got to leave you on a little cliffhanger. But I think we covered quite a few interesting topics here. Just in general optimization, not even considering SSE. So look forward to next episode. I'm Chili. Peace the fuck out.